Swayam Prabha. Digital India. Educated India.
How can we do calculations of non-prismatic members given our code provisions that are essentially based on uniform members? In the case of our column axial compression, you can say it's prismatic member subjected to a constant axial compression along its length. And so a lot of my discussion obviously will be in the context of the AISC specification, but this concept is more general than just AISC. It's immediately applicable also to if you're designing in the Indian standard or any other standard. And so the point I want you to bring away here is what's shown here. Basically, the limit states when we have axial compression and it's a non-prismatic member, or it's a member prismatic or non-prismatic where the axial force or stress is varying along the length. The limit states are essentially the same as for prismatic members in constant axial compression, but there's more to check. Well, why? Because the cross-cut section and or the axial force is varying along the member length. And so we've got more to check because of those variations. All right, so the bottom statement here is essential. What I want you to imagine is, suppose we're going to say, okay, we want to do a column strength check on columns in some structure. Sketch whatever structure you wish. Say, I've got a whole bunch of columns, I've got all these loads, and I'm going to do an eigenvalue buckling analysis on this group of columns, right? And from that, I get an eigenvalue, right? And we know that, so given these axial forces placed on all the columns, given the eigenvalue, the force in all those columns at buckling is the eigenvalue times that force, times that reference force, right? So then how would you check the strength of all those columns? I've got my elastic PE in each column, or I got my elastic FE in each column, the stress. And then you would take that to the column curve, be it the Indian standard or the American standard or any other standard, and you get a factored axial compressive strength of each column, right? And then you would then, when we put it together with everything else, you would say, okay, well, I've got what I call PU, the factored load demand, and is that less than the VPN, or in your case, the PN divided by the partial safety factor? If it is, then okay, I've got more capacity to take bending or whatever, right? Is that good? That's how we would check all those columns. If it's a non-prismatic member, think of each of the cross sections as like a separate member, and say, oh, well, let's see, we'd have to talk about, well, generally, how can we calculate gamma E, the elastic buckling eigenvalue? But if we have that, then I can get a stress at buckling at each of those cross sections. We'll treat each of those cross sections like a member. Do the calculation. And then the strength of the member is the most critical in terms of what gives you the largest PU to VPN. That would be the governing check, right? So you treat it just like you would treat a group of columns. That's it. It's a very simple concept. You could argue that, well, are we missing some things with that? Well, let's kind of look at it. We can ask some questions about it. but it turns out it works really well. Colleagues that have worked in this sort of area, particularly some colleagues in Europe, when they showed me what they have done, and we get into all these elaborate things about trying to account for the non-prismatic geometry, and it's very complex. This isn't complex. It's just treat each cross-section like the same way you would a bunch of columns. All right? So that's the point here. I think the other thing that happens if you're talking to engineers that are more familiar with designing hot-rolled structures where we don't have to deal with local buckling is, okay, that's nice if we've got non-slender elements, but once we get into tapered and stepped cross-sections, often we're talking about types of structures where we're going to be encountering slender plate elements somewhere along the length. All right, so I can now try to make it as complicated as possible. We can say, we want to check a frame. It's, oh my God, there's a lot going on here. But I can do an analysis of this frame that has all these multiple tapers and steps and steps in both plate thickness, steps in flange widths, steps in force, where force is coming in from a crane bracket there on the column. So all kinds of things going on in this frame, but if I'm I need to get a PU divided by VPN, that's the critical somewhere, then I know how to do that. So the next few slides basically try to amplify on that simple comment I just gave you. So this is in essence the process that the AISC MBMA Design Guide 25 uses when we calculate strengths there. We're looking at the concept just in the context of axial compression right now, but this same concept is going to show up when we say, oh, I want to calculate a strength in flexure as well, when we have non-prismatic geometry. Now let's focus on just getting an axial compression demand to capacity ratio, a DCR, at this point, PU over VPN. So here's some hypothetical tapered column with several axial loads coming on the column along the length. There's X's, maybe they represent brace points where we're preventing out-of-plane movement of the section. Looks like we've got there in the middle just maybe a brace point that's an attachment of a girt, maybe on the outside flange, but there's not a flange diagonal to the inside flange. Okay, so how do we approach this? Well, given this column, we can model it. Given the tools in Consteel, it's relatively easy to basically create a model of this column. And I can get an elastic buckling eigenvalue, gamma E. And so that's a constant for the whole thing. But now the demand, and so this is written to accommodate either ASD or LFD. So we have FR as the required stress and PR is the required load, but just you can replace those by FU and PU if you wish. That's for LRFD. And so at any cross section, gamma E is or we could say the force at elastic buckling is the factored load at that cross section times gamma E. Right? That's probably the simpler way to do, way I said it a few minutes back. Or the stress, FE at elastic buckling at that cross section is gamma E times the factored stress that we're trying to check. So that's the first point there, or the first bullet. But then now the axial load or the axial stress level, that's of course varying along the length. But if we focus on various potentially critical cross sections, we can basically look at each cross section and say, okay, what's the force or the stress, P over A? What's the effective area? And based on the calculations we've just been talking about, if it has slender elements. And then we consider that cross section like, okay, let's do a member design. I've got a member, a uniform non-prismatic member that has that axial force, that effective area, and has the gamma E from item 1 here. What's the strength? Okay, so again, any member that's subjected to axial compression, if we're getting our buckling load associated with the axial compression, it's got a gamma E by which all these applied loads that we're checking the member for scale to reach to their elastic buckling values. Now gamma E is one value, right? That's your governing eigenvalue. But if you look at the green graph or the red graph out to the side there, that's a hypothetical variation in axial load along the length and variation in axial stress along the length. And clearly, if those are varying like that, we multiply those values by gamma E, so the stress FE or PE is varying along the length. There's only one governing gamma E. So how can we evaluate the strength? Again, if you calculate that FE at a given cross section, then treat that cross section like a member. You've got your FE, you've got the effective area that you can determine at that cross section. You can apply the equations and get a ratio of PU to PPN. Did I say it in enough different ways there? Now, another way to put it, maybe once we've focused in. Now, you might say, okay, well, how many different cross sections do I have to check? You can determine that if you look at a given member, I'll show you something about that here in a minute. If you look at a ratio of PU to a cross-section strength, that gets you pretty close. If you can identify where that's largest, then zero in on that cross-section, just do the cross-section, let's do this calculation there. In general, the way the equations work in the AIAC standard, you may have a slightly larger value at another location, but the difference is going to tend to be very small. For using the Eurocode approach, or I believe it would be true also in the Indian standard, where you have a cross-section strength that would be impacted by local buckling calculations. So you got cross-section strength, now you hit that with a chi factor to get your overall member resistance. In that case, absolutely, all you need to do is identify, well, what's the critical cross-section? That's the one I want to do my calculation for to get a member strength. And then the gamma E pulls in all the attributes of the overall buckling of the member. So once we've identified that critical cross-section, so here, maybe we've got a tapered column like this, and so sometimes if you look at a tapered column, if the web is really thin up there at the top, you might have such a so significant of an elastic local buckling effective width reduction. Possibly that cross section at the top might be more critical, but usually it's going to be the smaller cross section at the bottom if the web thickness is constant here along the whole length. And so you go to that bottom section, you get your Basically, if you've got your ratio of your PU, PR is PU, over PYE, well, what's PYE? It's AE times FY. If you've got that and you've got gamma E, you've got everything you need to get a PU over phi-PN. And it works quite well in terms of quantifying the resistances. So here's where you might have questions of, oh, really? But gosh, the tapered member, we've got stresses that are varying quite significantly on the length. Isn't it very conservative to just use something that's based on uniform along the entire length? Take my word for it or check it out. You'll find that the calculation is generally pretty good. And here's basically where the recommendation is for practical purposes. You can identify the critical cross-section for any member as the one that has the largest cross-section utilization. Where is PU to the cross-section strength, PNS, based on an effective width reduction, if you wish. You can do that based on FY for getting your effective area. That's going to be the one in AISC that tends to be the critical section. This is where Eurocode or the Indian code, the way you have your column strength equations, actually works much better here. It's going to be that section, definitely, in your case. All right, so let's look at our crane building here, and I'll look to illustrate a few things here with this. So this is showing the calculations are performed allowable stress design, because this is an example out of the Design Guide 25, and the metal building industry asked me very forcefully to please do all your examples ASD. So I did them ASD here. So if we do the analysis, this is for dead collateral plus 0.75 uniform snow plus a critical loading condition from the crane. So we get the moment diagrams on the top. Here we got the axial force diagram in this frame on the bottom. And so in Design Guide 25, we were using an academic software that's my software at Georgia Tech called Sabre 2 to do the calculations. But I've moved away from Sabre 2 and because it's too hard to keep supporting a program like that. And I've become a disciple of Consteel. So everything I could do in Sabre 2, I can do in Consteel, and then a lot more. And I told Belinta and his colleague that, okay, yeah, I could do everything you're doing in my software, but I would need to quit my day job and work for about 10 years to get there. But Sabre 2 gives you a good result as well. So this is the first mode of buckling for this frame. It's a side sway buckling mode. And so the aggravation in ASD is, well, that 27.2, that's 27.2 times the working load level. If I take the alpha of 1.6 as what's needed to get to strength, then it'd be 17 or 27.2 over 1.6 would be the eigenvalue relative to strength. And then the second mode here is relevant. We'll look at some things with Consteel, where Consteel actually gives you an indication that, hey, here's your buckling modes in the frame, and so Consteel would give you comparable eigenvalues for each of these modes. And we didn't talk a whole lot about the buckling sensitivity analysis, although we had that selected in what we worked before. What the buckling sensitivity analysis tells you is you look at mode 1 for this, and it tells you, hey, your columns are what need to be designed here for mode 1. And then it tells you, yeah, the girders aren't doing much here in mode 1. I'm going to let Balint explain some of that in more detail next week. And the buckling sensitivity will tell you, oh, mode 2 is what you really should be using for checking the roof girders. So roof girders, the gamma E is much larger. You can see the sort of buckling mode we have there. It's kind of a braced buckling mode due to the axial compression coming from the thrust out of the foundation. Okay, now the other thing that happens commonly with these structures, see if I can make that a little bit larger. In a lot of situations, we may have the out-of-plane buckling really being the critical buckling mode. If we look at what we've got here, this is basically showing things if we're using the direct analysis method, where if we're checking a given member for axial compression, the routine practice in direct analysis methods, let's just use simply supported end conditions for that member. So essentially K equals 1 if it were a prismatic member, or just simply supported conditions here on our non-prismatic member. So that's what I'm calling gamma EL. And Sabre 2 basically shows that in plane gamma EL is quite large. And I can get a very simplistic estimate using the minimum moment of inertia, and it's still very large. So I know that basically the major axis buckling in a braced buckling mode on my column here is really not something that's significant. But out of plane, okay, so now I've got what's clearly a constrained axis buckling mode, looking at the buckling mode that's coming out of the software. And the eigenvalue for that is 22.5. And then Design Guide 25 has a lot of ways to try to get a hand estimate. They're very coarse estimates generally, but you can see that this estimate here is pretty close, 22.8. So out-of-plane buckling is often what's governing on these frames. So now how do we check this column? Now here in this case, we're going with an approach where we're going to use a different buckling mode for the top portion of the column and the bottom portion. So depending on the buckling sensitivity, you might conclude that you really should use the same for both. So I'll leave that to some discussion that we'll have with Balint next week. But what you can see here is for the bottom unbraced length, we're doing direct analysis method where we use a braced buckling mode for the in plane. Well, that's very high, even with the coarse estimate from a hand calculation. And the gamma E for constrained axis torsion is the governing gamma E. If we look at the top unbraced length, then the constrained axis torsion buckling at the top is very large there because it's a very short length. And gamma EL in plane is again the governing gamma E here. And so again, so there gamma E would be 135. So let's say we've determined what our, for the segments we're looking at, what our eigenvalue is that gives us our critical buckling mode. So now we need to determine what's the critical cross section that we should check. Where should we go to and say, okay, let's look at the force level, the effective area at that cross section, and then work the calculation from the standard provisions for the prismatic members to get a strength. Well, here in this problem, the problem includes self-weight, so the axial stress in the column is increasing even in the top part, even though it's that top part's actually prismatic. And so the critical cross-section is going to be from inspection just at the bottom of that top part. For the bottom unbraced length, it's hard to determine what might be the critical cross-section, but very quickly you can zero in I need to either check the column base or the top of segment A, and this is segment A is where there was a step in a transition in the web thickness in the column. And after performing the calculations for both of these cross sections, the cross section at the top there where we've got a transition in thickness, it gives us the largest demand to capacity ratio. So I want to show you, okay, how's that working? So this is kind of just rehashing what we talked about or looked at yesterday as a calculations with the W24 by 55 example yesterday. But here we're zeroing in on this cross section at a step in the web thickness, just where the thinner web there at that step, at about midway up the column. And so we have a axial force demand at that cross section of 31.9 kibs. We can calculate the gross area of that at that particular cross section. We can get an axial stress on the gross cross section. That's FR here. Once we've got FR and we've got the governing elastic buckling mode that was the constrained axis torsional buckling mode eigenvalue, we multiply FR by gamma E. We've got our FE at that cross section at incipient elastic buckling of the column. Okay, well, let's take that into our column strength equation. Fy over Fe, then the column strength is Fy in stress is Fy times 0.658 to the Fy over Fe power. That's 30.1 KSI. And once we have that, again, remember the unified effective width approach, we calculate the F critical or Fn on the gross cross section. Then we use that to determine what the effective widths are if we have slender elements in the cross section. So here, the web slenderness, H over TW, is 144. That's rather high. And if we check the non-slender web limit, 1.49 square root E over Fy, that's 34.2. So clearly we've got a slender web. And even if we look at the fact that, again, F critical is the way we're writing it here, but the current spec would call that Fn. So lambda RW squared Fy over Fn is 46.2. That the H over TW of our web here at this cross section is still substantially bigger than that value as well. So now we need to calculate an effective width of the web. So we'll use Dr. Schaefer's equation here for the elastic local buckling stress of the web, Fe script L, written in terms of lambda R. Okay, so theoretical elastic buckling is at a very low stress here, 5.32 KSI, and we bring that stress into Winter's equation with a C1 of 0.18. That's our C1 for a web in an I section. And so the web effective width is 10.5. Notice the gross width here is basically the width between the insides of the flanges here. If I can find my cursor, is 27. So this very thin web that has an H over TW of 144, there's quite a substantial loss in effectiveness of the web for uniform axial compression. Okay, now the flanges in this case were 8 by 3/4 inch and 8 by 1 inch. If we do those checks, the flanges are non-slender, and so, or they're fully effective. And so we can do area of each flanges, the effective area of the web, effective width times thickness of the web. We have an effective area. We multiply our Fn by AE, we get a Pn, and then we're ready now to calculate a PR over PC. If we're talking about allowable stress design, that would be basically the applied load that we're working with here, which we started out with, 31.9 kips, divided by Pn, 482 divided, and that we could write a Pn over the factor of safety here being 1.67. Okay, so we got 0.111. Well, that's a small number. Yeah, these frames are not are really dominated by flexure, but then we have a small amount of axial compression that we need to deal with. If we look at the top unbraced length, similarly we'd get a kind of working through similar calculations, we get P over PC of 0.037 up there. So that's even smaller. All right, that's direct analysis method. Again, remember, in direct analysis method, we did the analysis with a stiffness reduction. If it's a gravity, a frame like this is not going to be stability critical, so you're not required to put any notional load in unless it's a gravity-only load combination. In this case, it was a crane loading, I believe, with snow but no wind. So we'd say, okay, yeah, we would put on a notional load or an out of plumbness in the frame there from that. And so we're doing all that because we want to get a good estimate of what are the true forces in the frame at strength. But the more traditional approach is the effective length method, and so that would be more true to using the current Indian standard as well. If I can get to the right page here. So let's wrap this up here and then take a break with looking at the effective length method. So with the effective length method, we have an in-plane, a relatively low in-plane buckling load, or buckling eigenvalue, 27.2, but that's larger than the constrained axis torsional buckling load. So again, the out-of-plane buckling, constrained axis torsional buckling is governing. Gamma E is 22.8 for the bottom segment. For the top segment, we're using a different buckling mode, and the gamma E for the in-plane side sway buckling here is still the 27.2. The constrained axis torsional buckling there is quite large because that's a short segment. Okay, so clearly the lower eigenvalue there is the 27.2. So now if we go to check the bottom segment, it turns out that the calculation of the axial compressive strength ratio, or the demand capacity ratio here, for the bottom segment, it ends up being the same as the direct analysis method. Well, why is that? Well, the column axial forces are really the same to width at about 1%, using either of these methods. And the elastic buckling load ratio from constrained axis torsional buckling governs in both cases. So therefore, we're really getting the same calculation and same result when we do the resistance calculations for both. So that was the bottom. For the top, things are different though. When we do the direct analysis method, we're relying on the stiffness reduction and any out of plumbness or notional load to cover the in-plane stability. So it was a relatively simple assessment. But here for the top segment, in this case with the effective length method, it's the in-plane side sway buckling eigenvalue, gamma EX of 27.2 governs. And so we've got to do another calculation that's basically considering how everything's working with that side sway buckling mode. And so, all right, if we do that, it's the same approach again. We've got a PR at the cross section we're checking. We've got a gross area we can calculate there. We can get a stress, PR over AG. We can get an FE, that's gamma EX times FR. Now we can get an FY over FE. We can go to now this FY over FE is 2.49, so it's actually corresponds to elastic buckling. And so the column buckling stress from the column curve is 0.877 times FE. Both flanges of the column are slender, or non-slender, but the web is slender at this critical cross section. And so we're going to calculate the effective area at this cross section. And so this is basically repeating what we did earlier again. We have our lambda W of the web at this cross section. We have our non-slender limit, 1.49 square root over Fy. 108 is larger than lambda RW square root Fy over F critical, or Fn. So we need to calculate the elastic local buckling stress. That's 9.49. We use that in the effective width equation. Effective width is 16.5, where the gross width is 27. So again, effective area is similar to what we did before. Then Fn times effective area gives us a Pn. And then we close out by getting the ratio of PR to PC, or the applied load divided by the allowable load, Pn over the factor of safety, and that works out to 0.08. So hopefully we can see that once you have something like this, there's no. It's just like, okay, if I have a building with 1,000 columns, okay, I've got a lot of calculations to check all the columns, right? Okay, if you have a non-prismatic member, you have more calculations to check that member than if it were prismatic. But using this concept of simply saying, okay, I need to find a critical cross section, now treat that cross section like a column. What's the strength given the gamma E, given what's going on with the effective area and the stress level at that cross section, we can get our demand to capacity ratio. So pretty simple.